An electron with charge magnitude E and mass m is accelerated from rest through a potential difference V and then enters a region of uniform magnetic field B, where its velocity is perpendicular to the field. Determine the radius of the electron's circular path in terms of E, m, V, and B. So let's break this problem down into two parts. So for the first part, the electron is accelerated and it gains some speed. And after it is accelerated through the potential difference, I'm going to call that speed V here. And this is little v. The potential difference magnitude is big V. So that's something to keep in mind. And then after we find its speed here, then we can deal with all of the magnetic field stuff. So let's start by just figuring out what speed this electron gains after it accelerates. So we know that the change in potential energy, or electric potential energy, of the electron is equal to the charge Q times the potential difference. And here we are given that the magnitude of the potential difference is V, or this potential difference here is V. And we know that the Q, the charge of an electron, is actually negative V. Electrons have negative charge. So the change in potential energy is negative E times V, where V is greater than 0. So delta V is actually the final electric potential minus the initial electric potential. And here, in this case, it's positive. And the final potential the final electric potential is actually higher than the initial electric potential. And this is true because it's a negative charge. So negative charges move from low potential to high potential, from low electric potential to high electric potential, in the opposite direction of positive charges. So with this, now that we have the change in potential energy, and note that this change in potential energy is negative, so it's losing its electric potential energy. And since there are no other non-conservative forces here, we can use the conservation of mechanical energy, which says that the change in kinetic energy plus the change in potential energy is 0. So the change in kinetic energy is just 1/2 times mv squared minus 0. Since we're solving for, this is just the final kinetic energy minus the initial kinetic energy, and the change in potential energy is just negative EV. So now we can simplify this a bit to 1/2 NV squared equals EV. And this is the potential difference V. It's not the velocity V. So now we can solve for V. So after doing some algebra, we multiply 2 to both sides, and then we divide by m, and we square root to everything. And this gives us the velocity after it has accelerated. And that is the first part of this problem. So now let's move on to the second part, where we want to find the radius of the circular path. So we have the equation that the force vector on a charge due to some magnetic field B is given by the charge Q times the cross product of the velocity and the magnetic field vectors. So in this case, here the velocity I've drawn pointing to the right, and the magnetic field is going into the page. So, and we can use the right hand rule to determine the direction of the force. So here I'm going to draw this again. And if we sort of have V there, here I draw the magnetic field again. And so if we move in this direction, you can show that the right-hand rule gives the force vector here. But since the electron has a negative charge, the force vector will actually be pointing this way. And so as it moves here, it will have a force vector perpendicular. And so it may end up looking something like this in the next time step with a velocity this way. And again, if we repeat this, we will find that the force points inward, and this force always points radially in perpendicular to the velocity. And this is what constrains the electron to be moving in a circular path. And we want to find the radius of this path. So we can use Newton's second law and figure out the sum of all of the forces in the radial direction, and set that equal to the mass times the radial acceleration, which in this case is the centripetal acceleration, given by mv squared over r. And we want to solve for r. So let's figure out what this radial force is. So from here, we can simplify. We already have the direction, and we don't really care about the direction all that much. We just know it's going to be in a circle, and the force is going to be radial, pointing radially inwards always. So we can just find the magnitude of this. And the magnitude of a cross product is given by the magnitude of the first vector times the magnitude of the second vector times the sine of the angle in between them. And in this case, the magnetic field B is perpendicular to the velocity. So this theta is actually equal to 90 degrees, and sine of 90 is just 1. So we can ignore this factor here and just say that F equals QVB. And this is the only force in the radial direction. So we can just plug this in for the total forces. So we have that QVB equals mv squared over r. Now, we can simplify this and rearrange this. So the square cancels with this v. And then if we solve for r, we get that r is equal to mv over q times b. And here, q is actually the magnitude of the charge of the electron E. And we don't use the negative here since we only care about the magnitude. So perhaps I could have made this more explicit here. And so now that we have this, let's plug in the velocity here. So that's m, and the velocity is the square root of 2 times E times the electric potential difference, which is big V, over m over EB. And now we can simplify this a little by moving everything inside of the square root. So to move stuff inside the square root, we just need to square it. So this becomes 2m squared EV over m over E squared B squared. And this simplifies to this m disappears, and this E disappears. So we have 2mv over EB squared. And that's our expression for the radius. And now we can actually check to see if this answer is feasible for this problem. And we can do that using something called dimensional analysis. And also we can also check limiting cases as well in the end. Okay, so first let's start with dimensional analysis. So that basically says that the units of this left side, the r, must be equal to the units of this right side if these two are truly equal. So what that means is that the units of the left side, I'm going to denote by these square brackets mean that we are looking for the unit and not the variable itself. The units of the left side are just meters, since a radius is just a distance which is measured in meters. And let's figure out what the right hand side is. So we can let's start by finding the units of all of these values here. So m has the units of m are kilograms because it's a mass. The units of v, this is the electric potential difference. And recall that the electric potential difference is defined as the electric potential energy divided by the charge Q, which has units of joules per coulomb. And the joule is really a Newton times a meter. If you remember the definition of work, it's just Newton times meter. And a Newton can further be simplified as a kilogram times meters per second squared. And this is just from F equals MA. So if I clean this up a little, this becomes kilogram times meter squared over coulomb times second squared. And these are the units of the electric potential difference. And the units of E is this coulomb, it's a charge. And B, the units of B are given by Teslas, but that's not very helpful. So let's see if we can break that into more fundamental quantities. So earlier we used that the magnitude of the force is equal to QV times B times sine of theta. And now we can ignore sine of theta because it's just a number and doesn't have any units. And if we solve for B, we can find the units of B by finding the units of all of these quantities here. Since we know B must be equivalent to this, the units of B, which are Tesla, must be equivalent to the units of this. And so the units of force are newtons, units of charge are coulombs, and this is velocity here. So that's meters per second. And again, we can break down newtons into kilogram times meters per second squared. And now we can simplify this a bit. So this cancels, and also this cancels. So B is really just kilogram per coulomb times second. Okay, so now in the bottom, we actually see that we have a B squared, in fact. So the units of B squared are just kilogram per coulomb times second squared, which is kilogram squared over coulomb squared times second squared. So this gives us the units of B squared. So now that we have all of that, we can find the unit of this whole expression here. So let's just plug in the units for everything that we have found so far. So 2 is dimensionless, it's just a number. M has units of kilograms. The potential difference has units of kilograms times meters squared over coulomb times second squared. E has units of coulombs, and B squared has units of kilograms squared over coulomb squared times second squared. So now let's just start by simplifying this mess over here. So let's focus on all of these fractions and reducing these fractions out. So first, this kilogram times kilogram becomes kilogram squared. And then over coulombs. And then we have these two fractions, which we can simplify by moving Coulomb squared times second squared to the top. And we still have meter squared. And then these two move to the bottom. Okay, so already we can see some things beginning to cancel. So second squared cancels, kilogram squared cancels, and this in the bottom we have 2 coulombs, and that perfectly cancels with Coulomb squared. So all we are left with is the square root of m squared, which is just m. So the units of the right hand are also meters, which checks out with the units of r being meters as well. So our dimensions are consistent, and that gives us more confidence in this answer. So this is not something you have to do, but if you have more time, this is something you could try to see if your answer is wrong or not. Because if your units do not match, then your answer is definitely wrong. And one more thing you can check is maybe see what happens if, say, b approaches 0. If b approaches 0, then this bottom gets very small. So r becomes very large, and the radius is essentially infinite. And basically you just have this charge moving in a straight line because there's no force to really keep it in a circle. And this is just one of the checks that you can do. So these checks can be used to see if your final answer actually makes sense. And in this case, it turns out that this is the correct answer. And that is how this problem would resolve.